Good afternoon, everyone. Thank you for joining us today at the NPU Friday Noon Seminar Series. Today, we have the great pleasure of welcoming Dr. Pawel Mekarski. He heads the Radon Technical Operations section at the Radiation Protection Bureau at Health Canada, where he's jointly responsible for the National Radon Program. He's been there since 2009. And specializes in the measurement of environmental radioactivity from both naturally occurring sources and human nuclear activities. And I think that's what we're going to hear about today. So his talk is entitled Identifying Traces of Nuclear Events, Developing the Next Generation of Radiation Detection Systems for Environmental Nuclear Forensics. And with that, I'll hand it over to Dr. Mekarski.
Perfect. Thanks a lot for the introduction, and thank you for joining the seminar today. And as the title suggests, the seminar is going to talk about exactly that. To put it fairly basically, we're going to talk about how we can use the information that is present or that we're able to measure from the environment around us to detect, identify that a nuclear event is taking place somewhere in the world, and use that information to determine what that event is. And so, the talk, later half of the talk, once we go over the relevant background information, we'll focus a lot on how can we do better and a lot of the advancements that we've been achieved at Health Canada in developing more sensitive instruments and better instruments to be able to pull out more information that we can use for this purpose. And so this entire process is what we would call nuclear forensics. Before I get going, I will give a caveat that this is work that I was involved in leading during from 2018 through to 2022, after which I moved over to my current position managing the Radon program, part of the Radon program, like Peter mentioned. But I am still involved in this to some capacity and support when needed. The first thing we'll talk about is what is exactly nuclear forensic. It's basically like I described. If you wanted to boil it down into three simple steps, this is what you would get. Where one, you take a sample of the environment that's around you. Two, you would then use some sort of instrument to measure this environmental sample, identify any sort of nuclear material that might be in the sample. And then three, you would perform an analysis, which can vary from something that is very simple and automated to something that is much more complex and requires the amalgamation of a lot of different information to then either get evidence or indicate what might be some potential sources of this material, whether they're licit or illicit activities that we see in the world around us. And so over at Health Canada, we operate several different monitoring networks. These are the ones within the Radiation Surveillance Division that house this research program and has this mandate. You can see that these consist of stations scattered all around Canada, and you can see that they have a wide range. They cover a large geographic area, and depending on the specific purpose of each of these monitoring stations and what they are looking for, they might that also dictates the placement of these. For example, the Canadian Radiological Monitoring Network that looks at the radiation exposure of Canadians. You'll see that this network has stations that are around all the major urban areas where we have a majority of the population of Canada lives. For the fixed point surveillance network, these fixed point stations, these provide more real-time information about the radioactivity in the environment that they're placed in. And so, for example, these are placed, we have several of them placed all around, for example, the nuclear reactors that we have within Ontario and Quebec to get better coverage there. But the stations that we're going to be focusing on for the purpose of this talk, and these were largely the focus of the research that I was doing, are these four stations. And so these are the four Canadian CTBT stations that we'll explain in a little bit. And so these stations are part of a larger global network, part of the, are there to support the Comprehensive Nuclear Test Ban Treaty, which, thanks to this treaty and all of the preceding treaties before that, we no longer have widespread nuclear testing in the world, which is a good thing. Nearly all countries have signed and ratified the Comprehensive Nuclear Test Ban Treaty, and it is supported by this verification regime. And so this verification regime makes sure that countries are complying with this ban on nuclear testing. And so to make sure that countries are not testing nuclear weapons, you need to have a system that is able to monitor for that and identify and detect when these occur. And so that is part of what those stations are for. The verification regime doesn't just include measuring radioactivity in environmental samples, like we talked about a little bit beforehand. It includes other various different technologies. And so this includes systems of seismic sensors or hydroacoustic sensors that will measure the vibrations and other signals that could be given off by potential nuclear explosions. And all of these different technologies will go and they make up part of what is called the International Monitoring System. And so this is run by the Comprehensive Nuclear Test Ban Treaty Organization. You can see that all of these various technologies, all of these various stations are scattered all around the globe to be able to get good geographical coverage. And you'll see. And so we see that on top of the 4 stations in Canada, we have many more stations all around the world of these varying techniques. So now we'll talk about a little bit more of the challenges that you're faced with when you're trying to identify, a global, something that happened in the world, a global event that you might not necessarily be close to, and the information that you need in order to be able to do that, and the challenges that come from the uncertainties and everything that feeds into the models that eventually lets you determine the nature of these nuclear events and the location. So this is an example. So in this example, let's assume that in this Japanese station that's shown there, JPP-38, you had a detection, you saw some nuclear material that realistically you wouldn't expect to see in like the natural environment. If you were to then consider using all of the available meteorological data where the air might have carried some of these radioactive particles and where this air could have come from over the course of the entire past week, you see that this covers a good amount of the entire continent of Asia. And so this could be using just this one data point. This anywhere in this could be a potential source of where that radioactive material could have come from. By taking this information and combining this with all the information of the other stations, not only the other stations that might have detected the same type of material, but all of the stations that didn't detect the material and were able to, say with certain degree of confidence that they did not see a detection, and that's where the particles could have come from if they were there. If you combine all of that, you can better constrain this region. And so, for example, this example is one of the the Korean nuclear tests. If you take the combination of data for multiple stations and constrain it, you can get a region that determine the probability density that looks a little bit more like this. It's still not as definitive, but then when you add the other technologies and the information from the other technologies that make up the verification regime, in the example here, these are the seismic sensors. So you can see a lot of seismic activity along the fault line on the coast of Japan there. But you also see that there was a seismic activity that was detected at the center or pretty close to the center of the the region of interest there. And using those two and combining them, it gives you a better degree of certainty that the event originated from this source, using that information that you gathered across the the radionuclide monitoring stations, but also the other technologies. So now we'll talk, focus in more on what is happening within the 4 stations that we have in Canada and how those operate. These are very similar to the stations that are operated by other countries within the same international monitoring system, the same CTBT network. And we'll talk about how we actually do this in the lab, in the field, in practice, and then how we can do better and make that technology better. So clearly the first part, and so this is the first part of the nuclear forensics chain that we explained at the very beginning, is to sample the environment. In this case, we're sampling the atmosphere. And so what we have set up that you see in the bottom right is this air filter on this square mesh. And below that, you have fans that suck a large volume of air through this air filter within this little dome structure. And so to put it into scale, these samplers, so they're high volume samplers, they'll sample about 20,000 cubic meters or past 20,000 cubic meters of air through these filters over the course of any 24-hour sampling period. where any sort of particulate matter will then get deposited on the filter. And the idea is that any sort of radioactive particles that you have would also then be embedded in this filter. The next thing you do is you do some sample preparation steps, and these vary depending on the actual geometry that you have and the type of samples you're doing. In this case, what we do is we roll these filters up, we take them off the sampler, we roll them up, we place them in this hydraulic press, and we compress them down to this very small thin disc that's a couple millimeters thick in this plastic housing, which makes these a lot easier to measure, and it produces a more uniform sample geometry, which does help with a lot of the analytical work that we can then place on our detectors. And so what this does is it produces this little air filter puck. And this air filter, what it is it corresponds to an environmental sample of the air in that location in the world for that given collection time period, which is 24-hour period. And these are changed daily and collected daily all year round. So at each of these stations, so this is on location, these stations also have a high purity germanium detector located within that shielding structure. And then these samples are at the station taken and placed on these detectors and measured. And following that, you have subsequent analyses that are done. These analyses are fairly automated. They are reviewed by staff in our bureau as well. And then these identify the different radioactive isotopes that you might see in that sample, whether they're natural or human-made. And we are able to quantify the activity of each of these different radioactive isotopes to then provide to support the rest of the network and the verification regime. So before we get into the really the advanced side and the advancements that we can do to be able to measure smaller traces of nuclear material within these samples and also measure them more accurately, we'll provide a little bit more background starting from the basics on these actual radioactivity measurements before we get into the more complex gamma spectroscopy and other types of spectroscopy that we're performing and improving upon. And so any sort of nuclear material that might be present on that sample, and in this example, let's say we have a radioactive isotope that undergoes beta decay, it'll produce various decay products. In the case of the high purity germanium detectors, over the course of the beta decay, let's say this emits a gamma ray. And so that detector, that gamma ray, might interact with a high purity germanium detector, where the detector would then measure its energy. If you take a look at the very boring plot on the left, that is what we would normally represent in a spectrum as a single detection. And so this example, we had a gamma ray from this isotope that was given off with an energy of 804 kiloelectron volts, which is our unit of energy that we're using, and corresponds to a single detection within our detector. So a single count represented by the dot at that one bin within that spectrum or that histogram. Now, what happens is as you measure this over the course of 24 hours, let's say, which is the typical measurement time at these stations, you will get many detections within your germanium detector. And if you add those all up, what you'll get an energy spectrum. And when you have this multiple detections at that same energy, so at that 804 keV, what that will result in over the end of that counting period is you'll end up with a peak in the spectrum. And so using the energy of that peak, which is very specific to the radioactive isotope that emitted it, you can then identify the exact radioactive isotope. The other thing that you will see is that on top of peaks, there's many other features in the spectrum. Most notably, you'll see that there's this big, large, broad continuum. And this all corresponds and adds into the radioactive background. So on top of having just radioactive isotopes, you have a lot of other particles that are interacting in your germanium detector, all contributing to the detection, all adding up together. So in fact, the spectrum that we are showing here is entirely background. So this is what the spectrum would look like when we measure absolutely nothing on our detector. And so this comes from various different sources, and we'll talk about how we can reduce and target the reduction or the contributions of these various different sources later on in the presentation, because that is really ultimately how we can improve upon the performance of these systems. But for example, a lot of the background will come from cosmic radiation, so cosmic ray muons, potentially from neutrons that are present within the laboratory or being produced within the laboratory, and also all the naturally occurring materials, because every material that makes up the Earth has some amount of radioactivity typically. And in these cases, especially for the more sensitive instruments, it can produce this background, which is anything that's not coming from within the environmental sample. So ultimately, the performance of the system and the ability of our detector to identify a radioactive isotope that we are looking for is how well it can define and resolve and distinguish this peak above this background. And so since we know that the energy is very specific to the radioactive isotope that it is emitting it would be the sensitivity of our system to measure any one radioactive isotope will depend on the isotope. And so we'll have a range of sensitivities, and we typically define them per isotope. And so the consequence of this, since we're always seeing these detections, is that in reality, we can never measure nothing. So we can't ever say that we measured none of this radioactive isotope, because it's possible, if you imagine here, that your signal or the amount of detections is just much lower than your background, in which case you don't see it. So what this means in practice is we can only ever set an upper limit on the amount of that isotope that could have been present in the sample. Otherwise, we would have had detected it. And so what this is called is the minimum detectable activity in the field, so the MDA. You'll see this come up a lot as we compare the performance of these various different systems. And it is largely determined by the amount of these background detections that you get in the region where you would expect a peak from the specific isotope. So in this case, the sensitivity to cesium-137 of this sample would correspond to the number of detection, or be proportional to the number of detections in that region around 661 keV that we have highlighted over there. So then here comes where all the improvements can happen. So in any of these systems, any of these measurements that we have seen, there's two major ways to improve the performance. Improving the performance just means we want to be able to distinguish more of these nuclear materials. The one way that you can improve upon this is you can increase the peak size. And so if you measure more radioactive isotope, you can imagine that it's easier to distinguish a larger peak over the naturally occurring background that you might have in your spectrum. The other thing that you can do is you can decrease the background. And so if you have that background continuum, if you imagine that we took measures to reduce it and put it back down such that we're measuring less of the naturally present radioactivity or naturally present detections, you'd be able to see a smaller peak above that continuum, which also helps you improve your sensitivity to the various different radioactive isotopes. And so you'll see these two themes continue as we go to the improvements. And so the first thing to note is that even within the international monitoring system, we already have a next level of improved measurement and improved capabilities. And so this is in the form of these certified radionuclide laboratories. And so there's many of these scattered around the world you'll see indicated by these triangles. And what happens is, for example, let's say that this Japanese station would have seen a specific radioactive isotope, one that would be of interest that might indicate human nuclear activities that you wouldn't expect to be there. What'll then happen is this isotope that was potentially identified within the spectrum taken at the station, this sample will then get sent to one of these certified radionuclide laboratories that employ better, more sensitive equipment to then get remeasured to be able to get a better distinction, a more accurate number, and potentially pick up more of these radioactive isotopes in that same sample. And so if you looked at the map here, you'll see that one of these triangles corresponds to, we run one of these in Canada. So this within the Radiation Protection Bureau of Health Canada. Located in Ottawa, we operate one of the certified radionuclide laboratories of this network. And so within this laboratory, we have the same kind of detector, very similar to what is operated at the stations. It typically uses just high quality commercially available equipment. We have a much better shield that we see there and operates very similar in terms of measurement and analysis to the stations within the network. The way that it improves upon the measurements, or largely improves upon the measurements that the stations have been taking, is twofold. And so when the samples are sent to these laboratories, they are measured first for a week as opposed to a day. And so the longer that you measure the sample, you can imagine the more detections that you would get that contribute to the peaks, which also makes the peaks easier to see. And so this improves the sensitivity to these radioactive isotopes by increasing the signal size. The other thing is the higher quality and better and thicker shielding that we employ on these detectors also reduces more of the naturally occurring background radiation that we have in the laboratory that we see as compared to the station setups. And that decreases our background, which results in an overall improvement in sensitivity to these samples. So those are typically how the existing capability advancements are employed within the network. However, Health Canada has been, over the past many years, along with other countries, been developing the next generation of these laboratories and working to advance this and push this concept of remeasurement and using more sensitive equipment by employing a bit more of a complicated setup. And so this includes employing additional detectors. So far, we've only ever talked about having a single sample and measuring it on a single detector, producing a single energy spectrum and analysis. And then we've also developed a lot of advancements in the analysis techniques that allows us to extract more information of the radioactivity within the same sample, within the same measurement. And we'll see that come up a lot as we go through the various options that are available in these systems. And all this is really doing is it's still trying to take that fundamental thing of pushing the sensitivity and improving the sensitivity of the system. And so this is what this system looks like at Health Canada. It is fully commissioned and operational now and certified for use within a different part for different isotopes within the Comprehensive Nuclear Test Ban Treaty Organization. As part of this network, that's something that happened fairly recently within the past year or two. And at the heart of this system that you can see in the little copper enclosure is you have two of these detectors. So these are the exact same model of detector that we have within the existing certified laboratory at Health Canada. Around this detector, once again, we took a lot of care and a lot of time in selecting the shield that these things are going to be housed in. To go into a little bit more detail on the shielding, you could probably have a seminar all in itself on exactly what types of shielding you can do and the strategies you can do just in selection of material to reduce the various different components of your background. But you can see that this is a tiered setup. So if you work from the outside in, you can see that there's 4 inches of lead. This lead is very good, a very high density material that blocks out a lot of the naturally occurring radioactivity in the laboratory and a lot of particles. You'll see these 2 pink layers are 2 inches of borated plastic. And so the boron with a high neutron cross section is good at suppressing the neutron contributions to the background that you have. And then especially for some of these more sensitive lower background system, the innermost lead layer will be a specialty low background lead, as lead typically has naturally occurring radioactivity within it. And then some combination at the very inside of these various different liners. And so in this case, we have tin and copper. Around the whole system, so if you close the lid, close it up so that everything is surrounded by the shielding is then surrounded by these 3 black panels that you see. And so these are 3 plastic scintillator panels. They're designed to reduce the cosmic component. We'll explain shortly exactly how that works in practice within the analysis. And these themselves are all radiation detectors. You can see the cabling and they feed into the system. And so now we've gone from having a single detector to a system that has 5 of them so far. We'll keep going at the end too. And then lastly, this thing is all hooked up. It's all using the same commercially available electronics, though with a lot more custom programming and coding to operate the analysis the way we do later on. But as opposed to having these electronics collect all the data and create that energy spectrum, create that single energy spectrum, which is typically how they operate out of the factory, we have these electronics all operating such that they were, instead of just creating a spectrum as you take a measurement, they instead record the individual energy of each of the potentially millions of detections that you have over the course of the measurement period, and the time at which that detection happened within your detectors, which allows you to do more advanced analytical techniques that we'll see a little bit later on. So to go back to the cosmic suppression, so for anyone that's not familiar then with the logic that goes on here, what these allow you to do is they allow you to suppress parts of the background by looking for events or detections in any of these panels that happened at the same time as detections that you saw in the central detector, the ones that we're interested in. If you imagine that you place a sample, and in the case of this 2-detector setup, the sample would be placed right in the center with the 2 detectors then adjusted such that they're almost sandwiching the environmental sample, this air filter. You'd imagine that any radioactivity that is naturally present, so stuff in the sample, which is what we're interested in, that does not have enough energy that it could theoretically penetrate all of these inches of lead and outer shielding and trigger a detection in these cosmic veto panels, so these background detectors on this slide. So what we're looking for is something on the left. So any event that we see like that, we would keep within our data set. If we see events, for example, like those attributed to cosmic ray muons, where the muon will pass through both the cosmic veto panel and the detector and register a detection in both of them, that is something that contributes to our background that's not coming from within our sample. So we want to remove it. And so in this case, we apply logic and we would reject that event from our data set. And so after all of this, we can still construct an energy spectrum and we can evaluate, with the same measurement exactly how effective our veto panels are and how effective this active suppression of the background is. And so that's what this spectrum is showing. And so we collect all the measurements, and since we collect all of the individual detections of all the, the various detectors in their times, we can reconstruct this afterwards to get this. And you can see that you get a factor 5 almost reduction in your background after using the cosmic veto. So you get a substantial background reduction by covering the detector setup and using these 3 additional detectors, while losing almost no signal. So we've done lots of measurements, obviously, as we have been optimizing this setup, and we found that even though you're reducing your background 5-fold, you can sometimes accidentally still lose detections that come from your sample. But that signal, that's what we would call signal sacrifice, is less than 1%. And so well worth the extra effort that was put into this system. Now, what we do at the end of this, because ultimately the easiest way and the best way to, well, the most well-established method in within the network is we add these 2 spectra together. So we have these cosmic suppressed spectra that are much more sensitive individually than they used to be. And we have these 2 identical detectors that we've spent a lot of care in to make sure that they operate and have very similar characteristics, is we add these 2 together carefully. And we have algorithms that are tuned for this case. It takes a little bit more effort as well. But in the end, what this system and how this system operates is you still put a sample between these 2 detectors, you create a measurement, and it produces this single energy spectrum at the end, while storing all the other information for a more complicated analysis that we'll see in a second. And so essentially the system acts like a single detector would with double the efficiency. It measures twice the amount of radioactivity since you doubled up, while still having a much lower background. And so by producing the single energy spectrum, we can actually run the same analysis routine, the same analysis and processing chains and steps and procedures that we would for our single detector, which is beneficial. So to give a quick summary and put it back to how we improve upon sensitivity of these radiation detecting instruments, we see that the 2 detectors maximize the signal. And at that point, especially for the thin air filters, you basically have the sample entirely surrounded by detectors, measuring the most radioactivity that you can. You have the specially designed shield that further reduces the naturally occurring background passively. And then we have these cosmic veto panels that reduce the cosmic components of your background actively. And so that's good. So everything conceptually makes sense now. And so the obvious question is exactly how much better does this do? Let's put some numbers and see how much better we do when we're using these more advanced techniques and these better quality materials in the method that I just described on the system. And so again, we're going back to the MDA, and in this case, it's going to be quantified by the amount of, largely by the amount of detections that you see in your background region. And we can use that to compare it to our certified laboratory, the one with the CAL 05 tag there, of the single detector that we showed earlier. And so we do this, we can do that for, you can basically do it for any radioactive isotope, but we're going to do it for these two radioactive isotopes of interest that we'll see later. And so for barium-140 and cobalt-60 that you'll see us returning to, both of interest in terms of the comprehensive treaty monitoring network and what you're looking for when you're looking in those environmental samples. So if you do this comparison, you'll see that by employing these additional detectors and these more advanced analysis techniques and data processing techniques, you get about a factor of 5 improvement in sensitivity compared to this traditional lab setup that is already doing better than what is possible at the stations. And if just to like make it clear here, when you're talking about sensitivity and the limits of what you can detect, you want a smaller number. You want to be able to detect a smaller and smaller quantity of that radioactive isotope indicated there. So anything lower corresponds to a better radiation detection system. So that's great. So we've seen factor 5 improvement. So now what we have is we have an example of what that looks like within a real world sample containing some of this nuclear material that we're interested in. And so from a practical perspective, here we have a measurement that we took. We took 4 air filters from one of our Canadian monitoring networks from the East Coast. These were all put together on this dual detector system measured over the course of a week. And in this case, we have just a small part of that energy spectrum presented. And so here, we're looking for this sodium-22 isotope. So this is our isotope of interest that we're seeing. We expect that if sodium-22 is in this sample, we would see a peak at 1785 keV, which is indicated by that arrow. You can see that maybe, there's a suspicious feature, but there's nothing that obviously indicates by eye when you're looking at the spectrum that this isotope is present or this peak is present in that spectrum. And this corresponds to just using one of the 2 detectors on this dual detector system and not applying the cosmic background. And so from the same measurement, we can also take a look at what happens when you do apply and reject the events that were coincident with any of the veto panels, and then add the 2 energy spectra together. This same measurement, spectrum on the left, becomes the spectrum on the right. And so you can see that, before, where it was not particularly obvious that this material was in your spectrum and that it was in your sample, you can see that there is a very distinct, clear peak after you apply all of these improvements. And so these are the improvements that you would get over just operating a typical radiation detector in a laboratory. And it shows that using these kind of techniques, this is just a good illustrative example showing how you go from something that may not have been detected in your sample to something that you not only detected, but then were also able to quantify. Now, we have already compared the performance of this system to the certified radionuclide laboratory that we have at Health Canada. But over the course of that same comparison, we performed a benchmarking exercise. And so this benchmarking exercise in 2019-2020 was to take a look and evaluate the nuclear forensic capabilities, and so the sensitivity of the instruments, the radiation detection instruments, in many different Canadian laboratories. And so simply the way this was done is we took the same set of environmental samples. These samples did not contain any radioactivity. These were just air filters that were compressed, what we would call a blank, and sent them around to the various labs for everyone to measure over the same time scale on their instruments. And so if you take a look at the comparison of all the results that we got from that study, we have other instruments, many different instruments within the Radiation Protection Bureau, as you can imagine, between the various networks that the group operates. And you can see that they all kind of fell into this grouping there. The other thing you'll see is that and I forgot to mention in the previous time this slide came up, is the specification for what a radionuclide laboratory needs to achieve in order to be an instrument that can be certified and can take part in this international monitoring system. So you can see that there is some variation between them, and this is typically due to the various different detector types that you have, the various shielding types that you have. Some of these also did include a little bit of active suppression, one that is more commercially available. But all of the advancements that we previously described in our dual detector setup shows, again, consistent improvement over what can be achieved using what is typically found in these various different radionuclide or radiation laboratories. So now let's talk about and show exactly the power of the system and the power that the sensitivity gives us for a real nuclear event that took place in the world. And so here you can see the top of a news article that I pulled off a web page. So over the course of, during summer of 2020, there was a radioactive release in Europe. There's many news articles about it, and several European stations picked it up. And so not all of them were CTBT stations. So a lot of the countries in Europe also operate, similarly to Canada, their own national monitoring networks. And so the radioactive material was picked up that shouldn't have been there at some of these national monitoring networks. So what we did is that some of these countries sent us their samples after they measured them on their equipment to be measured on this more sensitive advanced dual detector system. And so the first thing that you will see is that from this measurement, you will see that one, you increased the number of isotopes. In this case, we added 4 radioactive isotopes to the list that previously were not seen in that sample just by having this improved sensitivity. But even the ones that you did see, because you are detecting more of them using this setup and more accurately, produces a more accurate number. So you're able to more precisely quantify the existing radioactive isotopes. And the precision is definitely helpful when you're trying to feed the best information possible into reconstructing and combining this with the other detections around the world to figure out the origin and nature of this nuclear event. The other thing that we can do that highlights the power of these dual detector system with all this extra information that we can have is we can take a look at the 2 detectors individually, something that is not really possible when you're measuring a sample just on a single detector in a lab. And so when we looked at the ratio of activity that we measured, and so basically the activity that the left detector saw as compared to the right detector, you'd expect for something that is uniformly distributed within your sample should have even activity measured by both of the detectors. And so for the stuff that is uniformly distributed, like the naturally occurring like isotopes that we have highlighted on the left side there, we saw that, yes, this is very true. We saw a very even distribution of activity. However, for all of the fission and activation products that we saw that were identified within the sample, we saw that this was not the case. And then sometimes the left detector measured substantially more or substantially less than the right detector in the system. The other thing that we saw is that groups of fission products or groups of products that you would expect or isotopes that you would expect to be produced together were and had very similar ratios. And so this indicates that rather than having this activity distributed fairly homogeneously throughout the filter medium, you had fewer hot particles in your sample, which is something that would be more consistent with this kind of nuclear release from these activities. The other thing that we can do and that we benefit from having these 2 detectors is now we can take that same logic that we applied to reject the background events and flip it and use it to be able to better identify the radioactive isotopes or more confidently identify them within the sample. And so you can imagine that, for the case that a radioactive isotope, instead of emitting a single gamma ray, emits 2 gamma rays or more gamma rays at the same time. If you're able to measure those 2 gamma rays simultaneously, it produces a very unique signal, a unique signature, and it's very unlikely for 2 background events to create this kind of signal within your setup. And so what this allows you to do is by using this is called coincidence detection or coincident detection. It allows you to unambiguously confirm that anything that you might have seen in that spectrum, if you're not sure about it, does come from that radioactive isotope if you're able to look for that isotope's coincident signature. Sometimes, and especially in the case of nuclear events where you can often get these kind of energy spectra with dozens of isotopes and hundreds of peaks, where many are interfering with each other and overlapping, and you have all the convolution algorithms that are running, it becomes hard to identify. But by using the coincident detection and looking for these specific signals, you're able to take a look and find that from a sample a lot more confidently. In the case of the example that I showed for this nuclear event, in fact, 5 of these isotopes, so about half of them, had emit multiple gamma rays when they decay. And 5 of these were able to be confirmed, the presence of which was able to be confirmed in the sample using this coincident detection logic. Well, also, while we're still talking about the same event in the same sample, give you an example of what this looks like in practice. And so within the sample, one of the last isotope you saw on that list, the scandium-46, corresponds to it produces these 2 gamma rays. And so you'd expect that you would see these 2 peaks. So one at 1120 keV and one at 889. Unfortunately, the 1120 keV peak, like I mentioned, is buried under one of the naturally occurring bismuth peaks. And so it's very hard to see because it is entangled with the naturally occurring radioactive background. However, if you look at the spectrum, the region in around 889 is fairly flat and fairly clear. And what our peak finding algorithm was telling us when it ran over the spectrum is that there's a feature. There's something that we can see at 889 keV, and it was telling us that it's peak. Now, that looks like something is there, but if you look at the rest of the spectrum that you see on the left, you probably wouldn't want to confidently report that you saw this isotope. You might still report it anyway. It would have a fairly high uncertainty. Hard to say whether this thing that was in there that produced this feature was actually the scandium isotope. But we can look for this coincident signal. So you can imagine that if you take a look and you see both of these gamma rays at the same time, like I mentioned, you can be a lot more confident that whatever this peak is, if it is a peak, comes from this exact isotope. And so the way we do this, or one way that we can do this, is we can gate on the 1120 keV peak. And so what this means is that whenever in this case, the left detector sees something that is 1120 keV, we can look at all of the events or all of the detections that happen at the same time in the right detector and see what that looks like, and hopefully search for this pair of detections at the same time. So if we do this, we gate on that peak, the top spectrum becomes the bottom one. And so here you can see that now, whereas before you didn't have a very clear signal, you have a very sharp, very clear peak at exactly the energy that you would expect if you had this scandium isotope within your sample. Obviously, you have substantially fewer detections than you previously had. But the thing to note is that when you're looking at, you can see that the background in the top spectrum, so even after all these improvements, even after the cosmic suppression, your baseline there still contains maybe a couple tens of thousands of detections. When you start looking at these unique coincident signal, the tens of thousands of background events look within that energy region then goes to nothing. And so you go from 10,000 to virtually 0 background in the case of some of this coincidence analysis, which you can imagine is very powerful and very useful to be able to detect these isotopes, especially as you start adding more isotopes and these peak interferences become more prominent. The other thing that we've been doing within our laboratory to advance these detections is to further on this coincidence detection scheme. And so here, instead of detecting the 2 gamma rays, you have certain isotopes, like a lot of the radioactive double gases, that will emit these kind of beta particles, will emit electrons as part of just natural beta decay. And so what we can do is we can use other detectors to measure these electrons and see if we can measure them at the same time as the detections within our high purity germanium detectors. And so to do this, what we do for these gaseous samples is we'll pump them into this little gas cell where each of these 2 sides of the gas cell corresponds to another detector. And in this case, this will be placed within the center of our detector system, where the 2 sides of the cell will detect the electrons, and any sort of X-rays or gamma rays will then be able to, since it is fairly thin, penetrate through and still be measured by our germanium detectors. And so by looking at the coincident signal between the electrons and the gamma rays, we can again help identify the radioactive isotopes, and what is sometimes challenging to separate, just measuring their gamma ray spectra only, into something that produces very clear, distinct signals. And so here you can see that this is a different way of representing these coincident events. So rather than gating here, we took our energy spectrum and put it into 2 dimensions, where the gamma ray energy is the vertical axis and the electron energy is the horizontal axis. And then in this case, you have your peaks end up being these little islands or these little regions or these bands, depending on the emitted energy of the electrons of the isotope. And so this allows us, and in this case, the highlighted region corresponds to an island or a little blob that corresponds to this metastable xenon 131 isotope amongst a sample with other various isotopes that do produce these kind of coincidences, which are the other bands that you see here. So those are the current advancements that we have accomplished in the laboratory. And so the question that we're going to talk about in the last couple minutes of the presentation is, how do we do better? We've already improved this background reduction by an order of magnitude, employed all these advanced techniques. However, and we saw this too in the spectra that we collected, is that, while we're putting all this effort into reducing our background, it was still fairly prominent. You could still see it. And that's why, while we can reduce the cosmic background in our laboratory, we can't fully eliminate it. The thing that I didn't mention is, in addition to like a lot of the shielding that we have specifically around the detector, the building itself acts as a shield from any sort of cosmic radiation that is coming from above it. And if you do the math for all like the thicknesses of the concrete floors and the steel and everything else in the structure, it works out to be about the same as if we placed this detector outside and had a tank of water that's 3 meters above it, shielding it from any incoming cosmic radiation, which is this concept of 3 meters of water equivalent shielding. Now, to take that concept of using the building as shielding material to the extreme, we're going to talk briefly about SNOLAB. And so SNOLAB, the Sudbury Neutrino Observatory Laboratory, which is near and dear to me since that's where I did my graduate work, is a laboratory that operates as a clean room. The entire laboratory is a clean facility, but it's located 2 kilometers underground in a mine, an active mine that's near Sudbury, Ontario. This has a lot of different experiments, some of the forefront particle physics experiments, among many other nuclear experiments taking place there, that take advantage of all of this rock that is above it. And so the rock between the surface of the Earth and the laboratory also acts to shield the cosmic components. And in fact, it shields out almost all of the cosmic contributions to your background. And this 2 kilometers, if you want to compare it to this 3 meters that we talked about, becomes 6 meters. It's the equivalent of having this lab 6 kilometers underwater. And what that looks like when you collect the same energy spectrum, because SNOLAB also participated in our benchmarking exercise that we described, is the bottom spectrum, where you can see now you reduce the background by another further order of magnitude, to the point where if you look at the higher energy regions, you have to squint to be able to see any individual detections. What this looks like when you put it back on the same sensitivity comparison that we did as part of the same exercise is, you can see that even though SNOLAB, which in this case was operating just single detectors that you would traditionally find in a laboratory, can outperform even these advanced systems that we've been developing over the past many years at Health Canada. The other thing that you'll see from this is that now we're falling into these kind of different bands of sensitivity. So we have the traditional lab systems at the top. Even within them, you have these kind of subdivisions for those that are maybe spending more time selecting their shielding or putting in some active suppression. You have this advanced detector technology that we spent a lot of effort in both the equipment and the analysis techniques, and then these deep underground laboratories. So then this begs the question, how far can we go? How much better can we improve upon in developing these very sensitive instruments? So you can imagine that by combining a lot of the advancements that we had within the Health Canada laboratory and taking advantage of that and locating this and profiting from the excellent ultra low background environment offered by SNOLAB, you might be able to do just that. And so that's exactly what has been happening since the completion of this benchmarking exercise as part of this safety and security program project. And so this project, part of this project, involved the commissioning. This project is aiming to increase Canada's nuclear forensic capabilities amongst, I think, 8 partners in total. The part of this project will see the commissioning of one of these advanced dual detector systems in SNOLAB, located deep underground, benefiting from all of this near zero cosmic background environment. And so the status here is that the system is set up, it's up and running, it's working. It is currently waiting on the shield to be delivered that we expect to arrive almost anytime soon, at which point putting all of these advancements in a zero cosmic environment, the expectation really is that at that point we will have this world-leading system in terms of the traces of radioactivity that it can pull out from these environmental samples. So that concludes this presentation, taking you through, this process of nuclear forensics, exactly how we do it, this information, along with, scaling these advancements, incrementally improving upon the sensitivity in these various different ways, and then putting it to the extreme environment there. And so ultimately what these systems will let you do is by providing the best, most precise information to the network will allow you to pull out and better identify, better locate, and better figure out the nature of the nuclear events that are taking place in this world, which unfortunately we see that they take place even still every so often. And then the other important thing too, and that we alluded to is, even if you have these sensitive systems and you don't see anything, the fact that you're able to say that something was much lower or much nearly zero is also hugely beneficial in being able to identify and being able to locate and identify the origin and nature of these events. So that concludes the talk. That's it. I have this additional slide here with the contact information for those that might be interested in following up of myself and also of the two people that are leading the various different groups that operate these networks within the Radiation Protection Bureau of Health Canada. I will take the chance now to advertise that we at the Bureau, well, the Radiation Protection Bureau, but the Surveillance Division as well, is always looking for qualified staff and students to take part and work in this research. And we do find that a lot of the nuclear work that we are doing overlaps quite well with medical physics. So please don't hesitate to reach out to us if you do have any questions afterwards. Thank you.
All right, fantastic. Thank you so much, Pawel. Very super interesting talk on some detector physics. We're open for questions. So if anyone has a question, please feel free to, if you're on Zoom, just unmute and ask it. You can type it into the chat. And for those in the classroom, I guess John can parole the room, but we're open for business. I had some questions while people think about them. It's interesting, this isn't a question, this is me just talking about myself, but on your first slide, you showed all the different locations of the monitoring stations around Canada. And I saw that there was one in Alert Nunavut, which is like the northmost one.
Yeah.
Once I saw that, I worked there. I was working at the Environment Canada lab, and I guess one of those pieces of equipment that I was taking care of was actively monitoring for radiation. So who knew?
Yeah, what you'll see with a lot of the equipment, especially for that network, a lot of it is fairly non-distinct. You would have, at Alert, it would have just been maybe like a 1 foot by 1 foot by 4 foot steel box that has an air filter.
Yeah.
And for that part of the network, those samples are all mailed to the Radiation Protection Bureau. So those collected, I think weekly, would get mailed over to Health Canada, where then we would process and measure the sample.
So I definitely remember
easier
doing
to miss.
that. I didn't know what I was doing. I was an undergrad co-op student. A lot of the equipment was like, do this once a week, and I guess that was one of them. So that's cool. I helped, I guess. We had a question in the chat from Malcolm. He asks, what role does AI have in pattern recognition and peak identification? Great question.
Yeah, and so and this is something that is true in a lot of fields that are developing, especially as AI is becoming more available. Certainly AI, especially machine learning and those kind of models, peak fitting and recognition is something that is being incorporated more actively. In terms of the one-dimensional spectra and peak identification, there's fairly well-established routines that have been used for, there's still always improvements to do, especially when you're deconvolving peaks. Those have been pretty well established. These kind of pattern recognition technologies would be very beneficial, and there are lots of groups that are looking into them, especially as you go into the 2D regime. You can imagine that, I showed a two-dimensional histogram for the xenon isotopes. If you take a look at what this looks like for the particulate side, because you can also make that for just the regular environmental air filter, that could potentially have hundreds of isotopes, it becomes a huge mess. And so it becomes a challenge. And so there is active work in it, though obviously with any of these, it's definitely, there are their challenges. I will say that it becomes substantially more complicated to calibrate your system and turn the two-dimensional counts that you see and the two-dimensional, like anything that you would translate from that image into an activity. And so typically when you're quantifying the activity, you're actually using a combination of both the 1D and the 2D, in which case you can still benefit from this.
Okay, nice. I had a similar question. I guess it was more just on the, you highlight the work done to suppress background, and that seems to be how you gain sensitivity, really. Are you already at the limit where, like, if the background is well understood, you can basically subtract it out, or is that doesn't really do much because the background is so variable?
Yeah. So I mean, with any of these radioactivity measurements, you still have a natural variability, and so the sensitivity is limited. When you get to the point of no background is where, I mean, that's as low as you can go, which is the case for what we see at SNOLAB for the higher energy regions, in which case you just have detections. And so at that point, they can't actually use our regular peak finding algorithms that do fit the background and then do subtract it out. As they try to identify these things, you have to use a completely new set of algorithms because everything breaks down when you don't have background contributions. But even in our lab, I mean, you can see that for these week-long measurements with our continuum still have, like, each region still having hundreds of background detections and things. Like, you can imagine that a signal that was at 10 detections or less, you wouldn't necessarily see there. So there's always these improvements to do. By the time you improve the sensitivity by having the two detectors, it's hard to collect more signal because at that point you almost have a 4-pi geometry surrounding the samples. But there's also, like, the thing that this doesn't touch on too is, I mean, and it kind of glossed over, is the stations. A lot of how you sample really dictates exactly how much radioactivity you end up putting on your sample. And so there's a lot of work in developing these high air volume samplers to collect most efficiently the most amount of radioactive matter in that short time period. So you can imagine if you pump twice as much air through, you can collect twice as much radioactivity, which then also improves your sensitivity when you're looking at what you can, like, when you convert the activities you measure to activity concentrations in air.
Yeah, that makes sense. Is that something you can quantifiably see at the different stations that are sampling at different air volume rates?
So you can see, so you can see that does, I mean, it directly impacts it because, I mean, ultimately you're just dividing by the volume that you can collect. There is differences, and so the groups at the Bureau are also looking into different filters to look at things that are more efficient. And you're always combining, like, more efficient filtering materials with filter materials that are more radio pure, because there is natural radioactivity on some of these filters, and it depends on how the companies have been making them, which all factors into, there's a lot of things that take into account there. But yeah, you can see, I mean, these big filters that cover a large area that allow you to pump more air through, you can do a little bit better than smaller filters that, don't have as strong equipment pushing them through.
Yeah, that makes sense. All right, great. We have a question from Liam. Liam, go ahead.
Hi. You were talking about the filters and other parts of the detector that might have natural radiation in them. Did you do any work, and maybe I missed this and you mentioned it, did you do any work to subtract that background that is known? Is there any way to calibrate, you take 100 empty filter samples and then you collect the background and then you can subtract that from your spectrum afterwards or something like that?
Yeah, and so you're absolutely correct. And so this is, I will mention in all of the analysis that this is something I didn't talk about there. The background subtraction, and so there's lots of, like, there's different backgrounds that the detectors can measure. So you have your laboratory background, which is largely what I focused on. You also do have the background that comes from the sample itself, with, like, the blank sample without anything inside, and then anything on top of that's radioactivity. When you do go to process all these samples, you do feed in all of these various different backgrounds that the algorithms will subtract. And so ultimately what you are, when you're doing the analysis, which is largely, especially on the 1D side, because it's so well established, automated, is it will take these backgrounds, it will subtract the detector background, it will subtract the sample or the blank sample, and do that as it looks for these peaks to be able to identify these things. But due to, like, the statistical nature of all of these peaks and variability that you see, I mean, the more things that you're subtracting off, the more of a choppy result you're left with at the end of the day. which then further complicates the finding. And so the best thing is to remove it if you can, using all these techniques, but then you still employ that. We still need to take a background. We still need to measure a blank when we're using this system, but it helps us to have all the other advantages as well.
Thank you.
Super. Were there any questions in the classroom?
Yeah, Felix has a question.
How often you guys do this measurements usually?
So for the stations, the measurements are done, they're sampled daily, they're measured daily. In the case of these certified laboratories, we get samples from the network. We get about 1 or 2 a month. Obviously, it's highly variable. They're not all due to having nuclear material that was identified or suspected nuclear material. Sometimes they, as part of a network, get sent to us for, like, one of these 1 or 2 might get sent as a QC check to, double check the quality of the instrument of the stations. But clearly, yeah, with a 1 week measurement time, you're limited in your ability, and so you save it for the most interesting cases.
I've got a question. Is there any value, or could there be any value in looking at the temporal evolution of the spectra, given that different isotopes have different half-lives?
Yep, and so absolutely. And so this is something that we didn't talk about at all, because the tools that we have developed, and we've been working with a lot of our collaborators internationally on this. You don't see this temporal evolution. It's hard to see it as much in the one-dimensional spectra when you collect it on the commercially available lab detectors. But obviously, with the being able to have each detection in the time, especially for the short-lived radioactive isotopes, a lot of which you do get released in these nuclear events, you can. So you can, using the analysis tools that we have, for example, look at it, like highlight a region of a peak, and then look at exactly how many detections you have in time over the course of that measurement, which, what you're alluding to is you'd be able to basically fit the half-life of that radioactive isotope over this 1 week period, which is another indication, similar to the unique signature of the coincident event, that you do, that it is a signal coming from that radioactive isotope, because that property is also unique to each isotope.
Thanks.
Great question, though.
Great. All right. Thanks, everyone. Well, if we're done with questions, I see we're after 1 o'clock. So let's thank Dr. Mekarski for speaking to us today. And I'd like to thank you all for attending, and have a great rest of your Friday. Thanks a lot. All right.
Thanks.
Bye. Thank you.
We do have one burning question.
Oh,
Okay.
Cross checking, like, how do you know if the other station reported the truth?